the last example showed that the size of the various harmonic components and the powers associated with the harmonics go down as the order of the harmonic increases. So, we should like to see how fast these various coefficients go down, and that is related to what is meant by convergence of the Fourier series. So, we should look at the convergence, should like to look at the convergence properties of the Fourier series. So, first let us consider this particular point. Suppose f of t is approximated by the Fourier series up to order capital N. That means we have C naught plus 2 Cn cos n omega naught t plus Tn. Now, if you take n from 0 to 1 to infinity, that constitutes the entire Fourier series. But now suppose I truncate the series at capital N. So, this is the approximated Fourier series. We take only a finite number of terms, and the difference between the actual f of t and the truncated Fourier series, we will call that the error E of t. So, this error now depends upon the value n that we take. Now, if you take the square of the error, integrate this from 0 to t naught and take its average, then this is referred to as the mean squared error, mean square error. So, the square of the mean of the square of the error, this is called the mean square error. So, we will see that this decreases with the capital N, that value of n that you take. Closely related to this, and actually this expression is equivalent to another term like this. Suppose you take the RMS value of the given waveform and its square, f RMS square. Assuming that f of t is a voltage signal, this represents the square of the RMS value of the voltage signal. And if this voltage is applied to a 1 ohm resistor, this is the power that is dissipated in that 1 ohm resistor. Therefore, if this is a voltage signal, f RMS squared can also be thought of as the power available from the signal. However, if you take only the sum of the RMS values of the various harmonic components up to n, that means you take C naught squared plus n from 1 to capital N, 2 Cn magnitude squared. 2 Cn magnitude square is the sum of the squares of the RMS values of the harmonic components from 1 to n, because after all 2 Cn equals square root of an squared plus bn squared. Therefore, 4 Cn squared is an squared plus bn squared, and RMS value is an squared plus bn squared upon 2. Therefore, 2 Cn magnitude squared is the square of the RMS value of the nth harmonic component, and therefore, the difference, this is the power available from the signal, this is the sum of the powers available from the various harmonic components up to order n. So, this quantity can be shown to be equal to the other quantity which we had written earlier. Both these will monotonically decrease with n. So, the larger the value of n you take, the less will be the discrepancy, the less will be the error, and the decrease is monotonic, and as you take larger and larger values of n, these terms go down. So, the next question that we would like to ask is, how fast do these Cn terms decrease with n? So, that is the next property of interest that we would like to know. So, the question that we would ask is, how fast do Cn terms, the coefficients, Cn coefficients decrease with n? We would like to give the answer in the following manner. Suppose we take a f of t has finite discontinuities. example, suppose I have a waveform like this, square wave, familiar square wave. There is a jump here, there is a finite discontinuities. For such waveforms, it can be shown that for large m and a constant m, the Fourier coefficients for large n are constrained by a factor like this. So as you take n to be large more and more, then the coefficients go down as 1 over m. That means the spectrum for this, suppose it is like this, the values of the various coefficients are constrained by a line like this, m by n. On the other hand, suppose f of t is continuous, but the derivative f prime t has discontinuity. That means the function itself is continuous, but then there is a discontinuity in its derivative. An example function like this will be like this. Suppose I have something like this. This is a periodic function, it is continuous, there is no jump anywhere, but if you take its derivative, the derivative here is like this, the derivative here will be negative, that means the derivative function of this will be something like this. So the derivative has a discontinuity, but the function itself is smooth. In this event, the various Fourier coefficients go down as m by n squared. That means that they decrease as 1 over n squared. That means the decrease is faster than in this case, because this is a smoother function than this. You can continue like this. Suppose you say the lowest order derivative, the lowest order derivative which is discontinuous is k. That means first k minus 1 derivatives are continuous. The first time a derivative fails to be discontinuous is order k, then it can be shown that Cn goes down as m over n times k plus n to the power of k plus 1. That means this is a much smoother function than the earlier one, therefore the decrease of Cn coefficients will be much faster. As an example, suppose you take cos squared omega naught t. This is a very smooth function. All its derivatives are continuous. And the Fourier series expansion really is half plus 1/2 of cos 2 omega naught t. So you have the DC term, you have the second harmonic term, all the other terms have 0. So you have really one DC term and one second harmonic term here. That means further terms are all 0. Because this particular function of time is very smooth, all its derivatives are continuous, therefore the Fourier series go down very fast, and in fact they become 0 after n equals 2. So this is an example of very smooth function. That means, in other words, to say, if the function is smoother, then the faster will be the rate of decrease of the Cn coefficients. That is the summary of what we have discussed under this head. The third question that we would like to ask is, what is the behavior of this function at a point of discontinuity? Let us say this f of t has a discontinuity at a point x. Now, if you take the Fourier series and evaluate the value of f of t at f of x, it turns out that the series, the Fourier series converges to f of x plus f of x minus divided by 2. The limit of f of t as you approach x from this direction, this value is f of x minus. The value here is f of x plus. So, depending upon how you approach x from the right or left, you get x minus or x plus. But the series will converge to midpoint between these two. This is the point to which the series will converge, irrespective of how you define f of x. So, you may define f of x as some value, not necessarily this, but as far as the series is concerned, it converges to this. Now, let us look at this figure where we took the Fourier series for a square wave and we have taken up to the 49th term. Now, the series converges to 0 at this point, which is the proper thing to do, which is the average of the left limit and right limit. But you would also observe that there is a small amount of overshoot just before the jump and just after the jump. And this overshoot is referred to in literature as Gibbs phenomenon, and the amount of overshoot is 9% of the total jump. And this is something which will persist no matter to what order of harmonic you go to.